All right, here's a second example of a trig sub. We're going to use that table. We're going to get the right substitution. We're going to go through all the steps again. This is something squared plus something. It looks like it probably fits the table. If I look at this, 4x squared plus 9, this is 2x quantity squared plus 3 squared. In the table, that would look like a u squared plus a squared. So if we look at the table that we have back in our notes, u squared plus a squared suggests that we make the substitution u equals a tangent theta. So for us, that's 2x equals 3 tan theta. 2x equals 3 tan theta. That's the substitution we're going to do. That, of course, means x equals 3 halves tan theta, which means dx equals 3 halves secant squared theta d theta. We need the dx because we're going to replace all of the x's in the original integral with things involving theta. So we need to replace the dx as well. So our integral now becomes, let's see, it's a 1. We got the dx, so dx is 3 halves secant squared theta d theta divided by, so 4x squared plus 9. So we have 4 times our x, which is 3 halves tan theta squared, 4x squared plus 9 quantity squared. Now that's all in terms of theta, and it all needs to be simplified. So let's go 3 halves secant squared theta d theta over, what do we have down here? I square the 3 halves, multiply by 4, and I get 9 tangent squared theta plus 9 quantity squared. If we've done the substitution correctly, this bit here that was ugly is going to simplify and look nice like it does here. That looks a lot nicer. Oops. So let's see, one more layer of simplification. Let me pull the 3 halves out. So we have a secant squared theta d theta, and down here, let me pull the 9 out. So that looks like 9 squared times tan squared theta plus 1. Right, both of the terms in the denominator here had a 9 in them, so I can factor that 9 out, and then I can factor it out by I can square it since it's all squared. So let's see, going back to the numbers, 9 squared is 81, 3 goes into 81 27 times. 27 times 2 is 54, so I think we have 1 over 54 times the integral of secant squared theta over tangent squared theta plus 1 quantity squared d theta. Now the next part of the table tells us what identity to use, and the identity is that tan squared plus 1 is secant squared. So this becomes 1 over 54 times the integral of secant squared theta divided by secant squared theta quantity squared d theta. Powers of theta are going to cancel now. I have 1 over 54 times the integral of 1 over secant squared theta d theta. That doesn't look like a great integral for us. I don't really love working with secants. I'm going to write that instead as a cosine squared theta d theta. So now it's a cosine squared. Now we know what to do with a cosine squared from the previous section. Again, these problems can be involved, right? We're doing lots of stuff. We've done a substitution. Now we have to go back and do a trig identity. We've already used a different trig identity. but cosine squared is 1/2 plus 1/2 cosine 2 theta d theta. So we do that integral. That's 1 over 108 times theta plus 1 over 108 times 1/2 times the sine of 2 theta plus c. All right. One more thing here before we actually move on to the next line. Another trig identity here is that the sine of 2 theta is 2 times sine theta cosine theta. And that's maybe the next most common identity that can come up after the ones we've already encountered so far this semester. So we're going to use that. Now finally we'll have a 1 over 108 theta plus, so this sine of 2 theta is 2 sine theta cosine theta. 2's can cancel, so it's 1 over 108 sine theta cosine theta plus c. So we've got our answer, our antiderivative in terms of theta. We really need it in terms of x. So we go back, remember what our substitution was. 2x equals 3 tan theta. So we have 2x equals 3 tan theta, or tan theta equals 2x over 3. Now tangent is opposite over adjacent. Again, SOHCAHTOA, right? So let me draw a triangle. Let me draw an angle theta. The opposite to the angle theta is 2x, and the adjacent is 3. And that makes this hypotenuse 4x squared plus 9. A combination that you remember from the original problem, right? Now, that's tangent of x. Our answer is in terms of sine of x and cosine of x and theta itself. So this is what we're going to do with the theta. Tan theta is 2x over 3. So theta is the inverse tangent of 2x over 3. And then from this triangle, we have sine theta. Sine is opposite over hypotenuse, so 2x over the square root of 4x squared plus 9. And cosine theta is adjacent over hypotenuse, so 3 over 4x squared plus 9. We're using the drawing and the angle theta, looking at the opposite side and the hypotenuse, the adjacent and the hypotenuse. This now is everything we need for our actual solution. We have 108 times theta, 1 over 108 times theta. Theta is the inverse tangent of 2x over 3 plus 108 times sine times plus 1 over 108 times the product of sine times cosine. So if I multiply this sine and cosine together, I have 6x over 4x squared plus 9 plus our constant of integration. We could simplify the fraction 6 over 108, but I don't see the need. We can just leave it like that. We've done the hard work on this. And that is our trig substitution. We followed the same steps. This problem was slightly harder than the first example because this problem wasn't just x squared plus something. It was something x squared plus something. That does make it a little bit harder, but we've seen how to do that. And that's why the table was written as something squared plus something squared. Instead of using x, we used u, just for this reason. And then the steps were the standard. We do the integral in terms of theta. We use the identity that the table promises is going to be useful. It ends up being useful. We use it. We get an integral that we can do. After that, we had to use a trig identity, another trig identity. But then we got our answer into something that we could deal with once we figured out what sine and cosine of theta are from the triangle. And if we have a theta alone, then we can use an inverse function in our solution, in this case an inverse tangent. So there we go, our second example with a trig substitution.